Hello, this is a short presentation about diffusion-based image-to-image translation by noise correction via prompt interpolation. I'm Jun-Sung Lee, and this work was done with Min-Soo Kang and my advisor Boyoung Han in Seoul National University. Text-driven image-to-image translation is a task of transforming input images into other images aligned with target prompt. The goal of this task is to change the region of interest and preserve structures of the object and other regions. Many approaches to this problem nowadays use diffusion models, and our method also uses diffusion models. In diffusion models, there are two key phases, the forward and reverse processes. During the forward process, the latent image is gradually corrected with noise until it resembles Gaussian noise. The reverse process then iteratively denotes the latent step by step to reconstruct a new image. In these processes, the noise is calculated by a shared unit, which predicts the noise at each step based on the text condition, latent, and current time step. Mathematically, its process can be expressed as in this page. Xt is the latent, epsilon theta is the noise calculated by unit, and alpha t is the coefficient. In fact, the problem of image-to-image translation is that the starting point of the reverse process x target and time step t, which is equal to x source and time step t, is different from its true position x target star at time step t. So we need to reroute the reverse process. To save the computational resource, we suggest a method without an additional training process. As you can see figure below, the quality of generated images is poor if we only use the target prompt embedding as a condition in a reverse process. One of the reasons is the abrupt transition of text embeddings. So we introduce the correction term using prompt interpolation to smoothly edit the source images. This is the equation of the noise used in a reverse process, which includes the key idea of a correction term. The first term is called the source noise, which has a direction for source images. We try to correct this term to change the noise of we want. And the second term is called correction term delta epsilon theta with coefficient gamma. This correction term determines the quality of the generated images, and it should be focused in the region of interest in source images. So, how to get a correction term without any additional process? In our method, the correction term is defined as the difference between two noises conditioned by the source embedding y source and the interpolated embedding yt. The interpolated embedding yt depends on the time step t, and this value can be calculated by interpolating the source embedding y source and the target embedding y target, and the interpolation coefficient is changed by the time step t. In the reverse process, yt is initially similar to y source, but after several steps, it is similar to y target. I'll talk about interpolated embedding yt in more detail. There are two cases, word swap and adding phrases. The word swap case just simply changes the word in source prompt, and yt can be expressed as a linear interpolation of y source and y target. Beta t is the coefficient that depends on time step t, so that we can gradually move yt from y source to y target. In the case of adding phrases, we found that token embedding using clean model is influenced by preceding tokens. For example, the first and second token in the source and target prompt has same embedding, while the embeddings of other tokens are different. So yt is calculated considering the position of tokens in this case. This is the figure visualizing correction term in 6 different translation tasks. Experimentally, we found that the correction term only focuses on a region of interest in the source images. And this is the pseudocode of our algorithm called PIC, Prompt Interpolation Based Correction. First, the forward process is done during large t steps. Then we calculate the noise epsilon theta hat during tau steps in the reverse process, using correction term via prompt interpolation. After tau steps, the naive reverse process is performed. We follow this pseudocode in all experiments. In the experiments, we use 250 images from the line 5 dataset in 6 tasks each. Stable diffusion version 1.4 with 50 diffusion steps is used for fast inference. We also set default hyperparameters as in this page. We compared our method PIC with other image translation models, prompt-to-prompt, plug-and-play, and pix-to-pix 0. We set 3 metrics for the comparison. First, Clay similarity calculates the alignment of target prompts and generated images. Second, background distance calculates the distance of backgrounds in source and target images using LPIPS. Finally, structure distance calculates the structure distance in source and target images using self-attention maps in VIT. This is a quantitative comparison with other algorithms. Our method PIC achieves better performance compared to other methods in string metrics. And for qualitative comparison, our method PIC preserves structures and backgrounds of source images and translated images better than others. We also test our methods by integrating other methods. As you can see, background distance and structure distance improve when our method is integrated with a slight decrease in Clay similarity. In the figure, PIC increased translation performance when integrated with other methods. And we measured the inference time on the A6000 GPU. The inference time of PIC is 18.1 seconds, which is much faster than others. Finally, we consider using only noise correction or prompt interpolation in our method. As shown in the table below, we found the PIC using both noise correction and prompt interpolation achieves the best performance. If you have any questions, please contact us via this email or GitHub. Thank you.